Now, what I want to show you is actually some more advanced features we have. So based on time, I'm not going to give you a whole background into what spatial stochastic simulation is, but the premise is that we're going to use the reaction-diffusion master equation, and that if you have, say, different parts, for example, if you have, say, mRNA produced in the nucleus that needs to diffuse out to the cytoplasm, and then in the cytoplasm it'll make proteins. The proteins then diffuse back into the nucleus to affect your species that are DNA, and you don't want your DNA to leave the nucleus. Those all happen, and the basic idea is that you divide your spatial domain into voxels, and each of the voxels has to be small enough to be well mixed. And this is, of course, a very loaded term. There are a number of different details when it comes down to that. And then the other detail is it's very expensive, and it scales. It can become diffusion dominated very quickly, and it sort of scales with the number of simulations. But we can do spatial stochastic simulations in StochSS. So this is the cylinder annihilation demo that I'll show you here in just a second. Okay, so, nope, that's wrong. Okay, so in StochSS, I'm going to go back to my projects. I'm going to go into the mini tutorial live. Spaces are obviously not a problem. And now what I want to do is I want to create a new spatial model. You can see we have beta listed next to this. And I'm going to make this spatial birth death. Okay, so my spatial birth death editor looks very similar to the editors we have, except now we have this domain, and our initial conditions will be slightly different too. In a spatial, your initial conditions are a little bit different. So now in my domain editor here, I'm sorry, I have to say, let me build a new domain. So right here is where you would show what your domain looks like. We don't have anything in there yet. So we're going to build a new domain. And let's see, I want, within this, there's going to be a lot of details, including pressure, speed of sound, density. These are all details that are going to come along. We can also have gravity, and I'll show you the effect of that. So we're going to have to specify the limit of our domain. So I'm going to go from 0 to 1, 0 to 1, and then z-axis, I'm going to make this semi-2D. By making this 0, 1, 0, 1, 0 to 0.1. So the z-axis is very flat. So this is going to be sort of more or less a sheet. And then I have to sort of assign types. And by types, what I mean is when you're making a spatial domain, you need to give physical properties to the mass that your domain is. So each of those properties are discretized into a number of particles. Each one of those particles has these properties such as mass, volume, viscosity, which is represented by nu. So go ahead and make this fixed, submit, and I'll give this a name. I guess I'll make this name stuff. And then I could add another type if I want, but I don't need to do that. So I'm just going to go ahead and delete this type here. So I've got my one type of matter within my domain, and you can see I haven't actually added anything to my domain yet, so I can go down here, and I can either create particles singly one at a time, give it an X, Y, Z position, and then you can see I can assign a type to that, or give it individual pieces here. Once we have some things, we can select them, we can set particle types, upload in a file, but I'm going to go ahead and create a 3D domain. So number of particles along the x-axis, I'm going to do 10. Number of particles along the y-axis, I'm going to do 10. Number of particles along the z-axis is going to be 1. So this is going to be a 10 by 10 by 1 grid of these particles. And by particles, I mean voxels. Domain limits, we have to set those again. So this is 0 to 1, 0 to 1, and 0 to 0.1. And it's basically going to put 10 particles between 0 and 1. So one of them is going to be at 0, one's going to be at 1, one's going to be at 0, one's going to be at 1, and then there's only 1 in this dimension. Click on Advanced, and I can pre-assign all of these to stuff. and I'll click Build Domain. And you can see here, now I have my sheet of particles that is my domain. And I can select one of these particles, click that one, go back down here, edit selected, and you can see this is of type stuff. It has mass 1, it has volume 0.001, which is, of course, a function of the area that it was specified in. And, you know, 0 viscosity, and the fixed is set as true. And by fixed, what I mean is not moving within the domain. So F equals MA has no effect on it. So this is what I want. So I'll save this to my model, and then scroll up here and go back to spatial birth death. And now when I expand this, you can see that I have my domain here. So simply creating a 3D domain was all we want to do here. So initial conditions. Now, with a non-spatial, initial conditions is just a number, but with spatial, you need to put a number in a place, an XYZ coordinate. So we've provided 3 different functions that you can overlay on top of each other to do this. One way you can do it, if you're doing things randomly, is you can just scatter some number of these biochemical species within the domain. Or you can place some number of species at a specific XYZ coordinate. This is helpful if you do multiple places together. Or let's say you want just a uniform distribution, where you can put X of these inside of each one of the voxels / particles. So I'm going to scatter, I'm sorry, I'm out of order here. Variables, right? So with depth, we were talking about rabbits. And then diffusion constant, I'm going to set this to 0.1. This is how fast these rabbits are going to move between these various different particles. Okay, so now I can add an initial condition, and I will scatter. You can see I'm going to scatter 100 rabbits in the domain, and if I have multiple different types of mass, I can choose to scatter it across all of the types or across only some of the types. So I'll go ahead, save these variables. This is taking quite a long time. Let me see if I can. Yeah, again, I apologize. This is this usually takes no time whatsoever to do this part. Those projects, okay. Spatial birth death, all right. The domain is still there. We didn't get to add our variables. Let's try it again. Rabbit, diffusion constant 0.1, save variables. Perfect. Okay. Initial condition, add initial condition, scatter, rabbit, got 100, save initial conditions. All right, parameters. have two parameters, k birth. That value is going to be just like yesterday, 10, k death, 0.1. Save parameters. Reactions, same as before. So we're going to have a birth reaction. Nothing goes to A. I'll just keep it R1 for now. And then the only detail here is reactions can be specified for only specific types. So I'll show you that in another example in just a minute here. We're going to produce rabbits at k birth. We're going to lose them at k death. Perfect. Okay. Create rabbits, destroy rabbits. And then time span. Sample frequency 1. All right. Simulate, preview. All right, we've got 100 particles. Well, fantastic. I'm going to go ahead and go to GitHub. Not GlassPy 2, but instead to the StochSS tutorial. So I'm going to go ahead and click on this link right here, this spatial link. So this is an open.stochss.org link. So this will bring me right back here. And all right, one more time. All right, we're into our spatial project here. So yeah, I'm very sad I couldn't show you the spatial birth death, but I can at least show you some cylinder annihilation. So in this one, I have a much more complex domain. So this one is a cylinder, and the two ends of the cylinder are specified as different types. So I have different subdomains within it. So here we have middle, edge 1, edge 2. And you can see the number of particles within each of those edges, and you can click on one of these particles here and see what's going on. So if I click this one, this is of type edge 2, click on one, that's a middle, click on one, a green one, that's an edge 1. And this is great because, and then I have two species, A, diffusion constant 0.1, B, diffusion constant 0.1. My initial conditions are nothing at all. I have a reaction and two creation parameters. And my reactions are, for R1, I'm just creating A, but A is only created in edge 1. And then my second reaction is I'm creating B. B is only created in edge 2. So one side creates A, one side creates B. A and B then are able to diffuse throughout the domain. And reaction 3 is A and B together annihilate each other. So this is what I call the annihilation, cylinder annihilation demo. And then I run preview. Just wait a little bit for this to run. Okay, perfect. All right, you can see that we still have our cylinder here. We can move it around. And then I'm going to be looking at the species A, and I'll hit play here. And you can see that the values all go to 0. And then you're starting to get a little bit of color on the left side, but none on the right side. And then as we go along, you can start to see the gradient of color that's going to extend out into the cylinder. So that gradient of color is showing us that diffusion is working. The fact that it only goes to exactly halfway, to exactly the x equals 0 point, shows us that there's also B in there, and the A and B are annihilating right in the area where x equals 0 when they come together. So this is our example of a spatial simulation. I can't if I pause it, then I can move this around. And now you can see, I'll zoom in a little bit, just the difference in the values of this. So high values, medium values to low values. So this is a example of that. What's my next piece here? I wanted to show you, we have what, 15 minutes left, or 10 minutes left. I guess I am going to jump to sort of some of my pre-done ones here and show you something a little bit more. So the first thing I'm going to do is, we don't have the feature that allows you to export this directly to a notebook quite yet, but that feature is coming soon. So this notebook is running not on StochSS Live, but instead just on my local computer. I wanted to run these ahead of time just in case something went wrong like it just did. So I feel prepared for this. And this notebook is that exact same model, but instead what I want to show you is that I have this external mesh defined. In this case, it was defined using Phoenix, but it's an XML sort of general style mesh. We can just read that mesh in. So this whole thing is done using SpatialPy. So SpatialPy does this simulation here. So we import this. We've got our plotting set up here, reload. Then over here, these are functions that are going to define those 3 domains that we saw before, right? So we have the middle. This class extends SpatialPy.geometry, and it has a single function inside, and given a XYZ triple vector, just tell me true or false, is that XYZ vector inside this domain or not inside this domain? And then you can just color them that way. We make our cylinder demo 3D model, extending SpatialPy.model. We define our species. We set our types using this up here. We import our mesh using the mesh import thing. We restrict the movement of those species to, well, in this case, we're going to restrict A to 1, 2, and B to 1, 3, where 1, 2, 3 are defined here. Some debugging stuff here, but here's our parameters, our reactions, our time span. Do the same thing where we do a model.run here, or create a model. And then we do a model.run. In this case, I instantiate the solver object directly and call solver.run, but under the hood, it does the same thing. And then I do some post-processing here. And this actually proves to me that this works correctly. So this is the time average of the simulation. So here's the x-axis. You can see that the A starts high on the right and goes down. B, it starts high on the left, goes down. And then this is the total population over time. And then I can just plot individual steps. If I want, I get these nice things here, and I can plot types to show the different types. And then here's another example of that distinguish. So here, so here's an example of SpatialPy, spatial stochastic simulation. And actually, to make the point, it does stochastic simulation and deterministic spatial simulation both at the same time. So you can look at the same species deterministically or stochastically, although the hybrid method is not implemented within this at the moment. So SpatialPy, cellular demo example. This next thing I wanted to do was show you a very different thing. So with this one, I showed you how to build up a domain. I showed you how to import a domain using an XML mesh file. In StochSS, if you're editing the domain, just hide this, edit domain. Here you can import mesh, and that will import that mesh right there for you. So that's what that is. But sometimes we want really complex geometries, and systems biology has these extremely complex geometries. So I want to show you what I think is maybe the most complex geometry. Now, this notebook takes over an hour to run, so I've already run it. So I don't want to change anything. But what I've done is I've made an image out of a font with the words Spatial Pi. So this is the physical domain that's going to go on, or it's the initial conditions of all my particles here. And then I have these boundary condition classes. So I'm going to have a hard floor or a bouncy floor, and they simply they return an expression that works on the interior simulation. And then I set up my Spatial Pi gravity model, and I say, here I'm going to make a mesh with sort of no items in it, and then use a programmatic thing to set the vertices, the X and Y vertices, the type, mass, volume, and nu of each one of these to this set of points that I derived from here. So basically, I'm setting all the mesh points here. I'm setting the time step, number of time step size, number of time steps, and output frequency directly here. And then importantly, I'm setting this to be a static domain equals false. What that means is f equals ma is now going to apply to this. And when I say f equals ma, the most important piece here is this gravity. So in the y direction, I'm going to have a -1 force that's applied to every one of my particles. And those particles are then going to drop. I'm same as before. I make the model object. I can make a solver object on that, call compile separately from run if you just call these together. But either way, I call the run method, and you can see this took 1 hour and 12 minutes on my computer this morning. Here is the initial plot at time equals 0. And here is the animation. So I can do result.plot property. Type is just everything animate equals true. And I can hit play. And you'll see this will move very slowly. So this is just an animation of the actual f equals ma simulate. F equals a goes on here. You can see it hits the floor and it bounces up because we have the bouncy floor boundary condition. But I'm going to go ahead and hit pause because I've actually done some post-processing to make this look a little bit better. Here's that exact same movie sped up. So you can see those particles are not aligned in any way. They hit the floor, they bounce again, and they bounce again, allowing us to have our nice Spatial Pi gravity model here. Great. I'm going to keep going because I want to bring up this next model, which again takes forever. So this model is by a very talented student. He did his senior thesis here at UNCA. He made the model of a weir. Now, I didn't really know what a weir was, but it's kind of like a dam, but except it doesn't, water always is flowing over it. So it's something like this. And, in honor of my colleagues in Sweden, I wanted to mention that there is a weir on the Uppsala River that's, right downtown, and it looks just like this. So all of these, you can look at our weir notebook that is in the example notebooks on Spatial Pi on GitHub. And I've done some very similar things here. We import Spatial Pi. We make a boundary condition class called teleport. Now this basically makes the right-hand side of this, any particle that moves over that teleports to the left-hand side. So we're getting just continuous flow. And we've got a hard floor and a hard wall. And in general, we're making the weir model here. And here again, we're making an empty mesh and then using for loops to go through the mesh to define areas of the top or bottom, or is this our initial area of water, or is this the step, the weird dam itself, or are these walls? We had the boundary conditions, time step size, output frequency, etc. And the initial condition looks exactly like this, and the final condition looks like this. And just to give you the animation in our last few seconds here, come on. All right, let me start this over. So this doesn't start at time equals 0, but instead you can see that there's a lot of water particles up on the wall here, and these particles are able to move around and have a fluid dynamics interaction with each other, and then they flow over the dam, and we've got lots of bouncing over here. When they reach the right-hand side edge, they could teleport back over to here, creating sort of a pressure well, moving these particles up and over the wall. So this is our F equals MA style fluid, particle-based fluid dynamics. And I invite you to look at this more. And we are working to get some of this working together. I think that's all we have time for today. So is there any questions from the audience before we wrap up?
It's a lot of content today. But
Indeed.
But then again, now you also know where to find us in case you try to use the software for some research. So just don't hesitate to reach out to Brian or me or Linda or Fredrik, or depending on what you want to do.
Yes, absolutely. We're all very collaborative, interactive. We've added many features that have been requested by external users. So if it's not doing something and you want it to do that, just go to GitHub and drop an issue in any of the various projects, and we'll be happy to respond to you. And want to make sure that you are using this.
Good. All right. Thank you so much, Brian and Fredrik. I think this was great. Lynn?